The glass prism shown right here has an index of refraction that depends on the wavelength of the light that enters it. The index of refraction is 1.5 for red light, which has a wavelength of 700 nanometers, and it's 1.6 for blue light, which has a wavelength of 480 nanometers. So you have a beam of white light, which is composed of all the different colors, that's incident from the left side. It's perpendicular to that first interface, so it passes through, and then it hits the second interface, where it's dispersed into spectral components, so all the different colors. But we're just going to focus in this problem on the red and the blue components. So for part A, determine the speed of the blue light in the glass. You have an equation for the index of refraction, which is n is equal to c over v. If you rearrange that equation for v, you get v is equal to c over n, where c is the speed of light, 3 times 10 to the 8th, divided by the n, which for the blue light was given as 1.6. So 3 times 10 to the 8th divided by 1.6 gives you a speed of 1.875 times 10 to the 8th meters per second. Part B. Determine the wavelength of the red light in the glass. And you have an equation for the wavelength when it enters a substance with a different index of refraction. Lambda n is equal to the original wavelength divided by the index of refraction. The original wavelength, which I'm just going to leave in the units of nanometers, so that the final answer can also be in nanometers, divided by the index of refraction for the red light, which was given as 1.5. When you divide those, you'll get an answer of 466.7 nanometers. And for part C, determine the frequency of the red light in the glass. So frequency is the thing that doesn't change when it passes from one interface to the other. So we can actually solve for the frequency of the red light in air, and then just say that the frequency stays the same when it's in the glass. So you have the equation C equals lambda f. If you just rearrange that for f, then f is equal to c over lambda. So the c, the speed of light in air, is 3 times 10 to the 8th, divided by the wavelength in air, which was 700 nanometers, which I'm going to write this time as 700 times 10 to the negative 9th, and that gives you a frequency of 4.29 times 10 to the 14 hertz. Remember, we said that what we just solved for here, this is the frequency in air, but it is the same frequency for glass. So that is still the correct answer. Now we want to take this figure and sketch the path of the red and the blue rays as they pass through the glass and back out into the vacuum. So we're not going to focus on the reflected light, and we're not going to calculate any angles. We just want to show the change in the direction of the rays at each interface and distinguish between those two paths. So when the white light hits that first interface, because it's perpendicular, it doesn't change angle at all. It just keeps on going straight through. So the white light, you can just draw an arrow that continues until it hits that interface. Now this one, the normal is perpendicular to the surface, so I'm going to draw a dotted line to represent the normal. Now the light does not pass straight through this point. If it passed straight through, this would be the path of it, going straight across like that. Instead, since we're going from a high index, the glass, to a low index, the vacuum, the light bends away from the normal. So instead of going straight through like this, it's going to bend away. But remember that the index of refraction is greater for the blue light. It's 1.6 as opposed to the red light, which is 1.5, which means the blue light is going to bend more. So the white light separates out into the components. The blue light is the one that bends the most, so I'm going to draw it down like this, going away from the normal. And the red light still bends away from the normal, so don't draw it going straight horizontally. You want to bend it going down like that. So you can just label them as the red and the blue. And again, you don't have to worry about calculating the angles as long as you have them drawn appropriately. In part E, we change things up a little bit because this time the light originates in the glass, it passes into this triangular wedge of vacuum, and then it comes back out into this glass area. So the initial part of the light, as it goes through, because it's perpendicular, it stays going horizontal. So just like in the last figure, nothing changes there. And I'm going to draw the normal again, which is the dotted line perpendicular to the surface. But this time, since we are going from a low index, the vacuum, to a high index, the glass, instead of going straight through like this, where it would go horizontal, the light actually wants to bend toward the normal as opposed to away from the normal. Going from low to high, the light always bends toward the normal. So I can draw the blue light. Well, actually, let's draw the red light first, because the red light is going to bend a little bit, so I have to bend it going up toward the normal. But the blue light is going to bend even further, but still not on the normal, so I have to draw that one kind of between the normal and the red light. And then you can just label both of those rays as the blue and the red. So in both cases, this one and this one, you see that the blue light bent more than the red light. It's just the direction was different based on whether it was going from high to low or from low to high.